So in this session, this session should give you a basic understanding of the physics that govern water's behavior. I know we've had certain situations where we get comments where they think people think water can do some unpredictable things, but in reality, water's pretty predictable, and in a sense of movement, it is it's, like I said, it's really predictable. And if we understand the basic math behind the science, that can explain some of those concepts. So let's dive right into the presentation. So water rules to live by. Water rules to live by. So water will always take the path of least resistance. It always goes from higher energy to lower energy. Water has a principle known as the no-slip rule. Water is incompressible. It is the universal solvent. And because of these things, and in a closed system, we know that the flow in must always equal the flow out. So with these concepts, we'll be talking about, and we'll start breaking them down one by one in the next coming slides. So the path of least resistance. Okay. So water always takes the path of least resistance. So water is very, similar to us when we are dealt with a stressful situation. What do? We try to look for the fastest and easiest way out of that stressful situation, correct? So that's the path of least resistance. Well, water does the same thing. It tries to look for a path that will pose the least resistance to its movement. A great example is a water main break. When the break occurs, we have massive amounts of water flowing out through the main break location. And we will talk about why it flows out and the location that that it is. So for that same water main break, so some of the reasons to the principle of why the water is flowing out at that location of the break is because it is flowing from a higher energy to a lower energy. Essentially, this is the path of least resistance if we understand how this energy works in a water system. So it could be stated that water leaves a pipe because it is moving from its potential energy state to its kinetic energy state, and ending at a static state, meaning no energy state. So what this means is, let's take, for example, I'm holding a ball up in the air. If I have this ball at a certain height, at a certain distance from the floor, and I'm holding it there, it is considered potential energy, or the ability to produce energy in the form of motion, right? So once I release this ball, I am converting that potential energy into kinetic energy, aka energy at motion. Once the ball hits the ground and it stops moving, then it's referred to as the static energy state, in which there's no movement at all. So again, potential energy is essentially stored energy that can produce. It has the potential to produce a certain amount of energy. Kinetic energy is the energy at motion. A moving object, has kinetic energy. Static state, or no energy state, is when the object is at rest. Now, this rule also takes into account multiple forms of energy. Examples are, pressure, heat, osmotic pressure, and friction. So we will talk about some of these in more detail in the upcoming slides. So the no-slip rule. When water cascades across an impervious object, what is the interaction between the water and the object? So what this means is, if I pour some water across something or across the surface, what we want to know is that water moving over itself or across the object? So again, if I take a glass of water, I pour it across a certain surface, is that first bit of water hitting the surface and then moving, or is that first bead of water hitting the surface, sticking to it, and then the following beads of water sliding over that? And the answer is it sticks to the surface, and the remaining water kind of cascades on top of it. So according to the no slip rule, what's happening is that when water comes into contact with a surface, it sticks to that surface, and as water is continually poured, it flows over the initial water layer. So this slip rule is important when we analyze the way that water flows through a pipe. So this is the velocity profile of water flowing in a pipe with laminar flow. Now, laminar flow meaning it's flowing in a predictable profile way, as we can see from the picture. Now, turbulent flow is when the water profile in the pipe is unpredictable. You know, you have water flow in a spinning pattern, etc. So when it is flowing in a laminar way, as in the picture, what's happening is the water is in contact with the surface of the pipe on the edges, sticks to that wall, and water further away or closer to the center that has minimal contact with that wall moves with more ease because of that reason. But the reason is because the interaction between the sidewall and the center flow is limited. The edge of the pipe has a higher frictional interaction. So the water, again, flowing down the middle of the pipe has the least resistance to this motion, therefore making it easier to flow down the middle. So essentially, it takes less energy to move the water down the middle of the pipe than it does to move it along the edge of the pipe. And therefore, the middle of the pipe is the path of least resistance. Now, what does it mean to be incompressible? Incompressible means that the volume of the incompressible object cannot be decreased under pressure, right? So in reality, if we apply high enough pressure to pressure 2, we will see a change in volume, but this change is, it's really minimal, down to a fraction of a millimeter. So we can consider that to be, negligible when we're dealing with millions and millions of gallons. So if we have 2 cylinders with a cylinder with a certain amount of water volume, and say we apply 1,000 pounds of pressure on cylinder 1 and 50,000 pounds of pressure on cylinder 2, there will be a negligible change in volume from one cylinder to the other. Now, why is this important? It is important because, unlike a gaseous substance where a relative large amount of volume of that substance can be packed into a relatively small volume container, as it is with like natural gas, an incompressible fluid such as water cannot change volumes. So on this basis, this is kind of the basis for flow in equal to flow out, as we will see in upcoming slides. So what does universal solvent mean? Well, how is it defined? So a solvent is able to dissolve other substances. Universal, the definition of affecting or done by all people or things in the world or in a particular group, applicable to all cases, right? So therefore, when you combine those two, universal solvent is one that can dissolve all substances. So given enough time, water can dissolve, anything. This is important to know because, water has a chemical reaction with anything it comes in contact with. So the universal solvent property of water is a base knowledge for understanding future discussions such as corrosion, soluble material, concentrations, water age issues, etc. So flow in equal to flow out. So flow into a system has to equal flow out of the system. If flow has, if flow has nowhere to go from point A to point B, then all the water that comes, into point A must be coming out in point B. So basically, if I'm getting 100,000 gallons into the system, we should be getting 100,000 gallons out of the system in some way. So since water can be considered incompressible, you can't put more in than what is coming out. You can't compress that to more coming in than is coming out. So basically what you put in has to come out in some way. So why is this important? It explains why we're able to have pressure in the system, why we're able to understand the direction water is going to go in the system. It explains how we can design our distribution systems. We can understand why we're getting the pressure losses in a certain system. Essentially, if flow is equal to flow out, then something has to be changing when pipe size changes, and it's important to understand what that is. So knowing this, we can predict what will happen when we have a change in pipe diameter or velocity. So from the equation, flow rate is equal to the velocity multiplied by the area, where Q is the flow, V is the velocity, and A is the area. So as we're working with pipes, they have an area associated with them, and they have a velocity associated with a certain flow rate. So with this relationship of flow in equal to flow out, and flow equal to the velocity multiplied by the area, we can, answer a couple questions. So let's do a couple of these practice ones. The first one, as area increases, what happens to the velocity? So as area increases, what must the velocity do to keep the flow rate the same? So say we have a flow rate of, 5 gallons per minute, which has to remain constant because flow rate is, flow rate in has to equal flow rate out. If we increase the area while keeping Q constant, then our velocity will decrease. Why? Because if we have this equation and we have the flow rate divided by the area is equal to the velocity, as we increase that denominator, what are we doing to the overall velocity as we're increasing that denominator? If we're having it higher, that means that the velocity is decreasing, right? So then the next one, as velocity increases, what happens to pressure? Now this next one is a little more difficult. As velocity increases, pressure does what? So because, this one's a little harder to figure out, since our equation of flow is equal to velocity times the area, it doesn't really have the direct correlation with that of pressure. So we will answer this question as we continue through the slides and explain a little more concepts, and we'll be able to see how pressure changes with velocity and area change. So what is pressure? Pressure is defined as the continuous physical force exerted on or against an object by something in contact with it. So basically, as we push more and more water into a distribution system, water keeps pushing against itself, accumulating, and water pushes up against the pipelines in the distribution system is what creates pressure. In the sense that we speak of pressure in the water business, simply put, pressure is the measure of energy that is stored in the fluid ready to be released. So you may ask yourself, how is pressure energy? Well, let's look at it this way. If I have a pipe and I'm pushing water into it, then I'm increasing the pressure within that pipe. So then say I break a hole on that pipe, then the water will come rushing out and slow down over time, right? So it does this because water wants to go from high energy to low energy. And once we introduce the break, water will flow out through that break, which is the path of least resistance. Essentially, as I continue to pump pressure into the pipe, I am building up that potential energy. And then once I break it, I convert that potential energy into kinetic energy, which is the the water spilling out. Once we no longer have any water coming out of the pipe, we have reached our static state or no movement state. So pressure is really the measure of energy within a system. Now, this is important for us to understand and lets us know how much energy we have remaining in our system. And the most common units used for pressure are PSI. And there are a couple more, which we will talk about. Now, what is head pressure? Head pressure is a concept that relates energy in an incompressible fluid to the height of an equivalent static column of that fluid, right? So what that means is if I tap into a distribution pipeline with a tube and I'm extending that tube, say I'm extending that tube up into the atmosphere, I can measure the pressure in the pipe with how high the water level rises in that tube. The pressure in the pipe will make the height of that water rise in the tube, and this height is associated with a certain pressure. So the higher the pressure in the pipe, the higher the water level will rise in the tube. As I decrease the pressure in the pipe, I will see a water level drop in our observation tube. So all we are doing is basically changing what we are reading on our gauge from pounds per square inch, the units, to head of water, usually measured in units of feet of water. So where does pressure come from? Well, it comes from pumps. It can come from storage tanks, hydropneumatic storage. So let's define a couple of these to kind of distinguish them. So pumps, sorry. A pump is used to create flow, and if you resist flow, it produces pressure. So as I flow water through a pump into a pipe and the flow starts to slow down, it starts to build pressure. As I can continue packing and packing and packing more water, it builds up that pressure. In storage, we have pressure associated with it because gravity is exerting a force on that body of water. And the higher we have water stacked in terms of height, the higher the pressure will be at the base of the tank. So the higher the pressure, the more water stored in the tank. The lower the pressure, the lower water level in the tank. And for that of hydropneumatic storage, so hydropneumatic storage, air can be compressed in a tank which has a membrane barrier separating the water from the air. So as we set air to a certain pressure, or we're pumping air into this membrane, we can then pump water to push up against that membrane and reduce the volume of air on the other side of that membrane, and therefore increasing the pressure of water. So as I open, say, a valve, the water will want to flow out because the air is exerting that pressure still on that water, since air is a compressible substance. It has that pressure, it has that ability to be compressed. So another way we talk about pressure is by total dynamic head. Now, the total dynamic head, while related to head, is not essentially the same thing. Total dynamic head is the sum of the total gains and losses across a threshold. We typically want to use total dynamic head when we are sizing a pump or a wellhead. So because it accounts, it accounts for the height we have to send the water up on. which is referred to as the static lift. So your your static height is where you want to take the water from, and frictional losses is any energy loss due to friction in that pipe. So this dictates how much total dynamic head one must have. So for example, if I want to have 60 psi coming out at my outlet from a well, well then I have to add up all my losses from head, from height, from lift, and from friction, and I place a pump in there that gives me my 60 psi at the top, minus all my losses to get the water to that point, and that total amount is the total dynamic head. Okay, so don't freak out. This is don't try to memorize this equation. It's just basically for conversation. So from previous slides, we want to try to answer the question, what happens to pressure as velocity increases, right? So now let's answer this question, from this previous slide. Let's first introduce a couple of terms. So from the equation, we can see here, delta P, that's the change in pressure. We have some of our constants, viscosity, length, flow rate, right? So let's first see what happens to area for velocity to increase. So if we want to keep the flow rate constant, right? So as velocity increases, what happens to that area? What happens to that basic area from that equation? So if we have area is equal to flow rate divided by velocity, if we increase that velocity, then we're increasing the denominator, right? As we increase the denominator, we are decreasing. We have to decrease the area to keep that flow rate to keep that constant flow rate, right? So if we look at the at the change in pressure equation as denoted here, right? If we decrease the area, right, as we're decreasing the area, we're decreasing the diameter, right? Which is the numerator part of the equation. So we are decreasing that numerator, and therefore we are increasing the change in pressure, right? That's increasing the change in pressure. That's a total change in pressure between those two distances. So let's say for example we have a decrease in velocity. Well, a decrease in velocity, as the velocity decreases, the area correspondingly increases to keep that flow rate the same. So if we have an increased area in the numerator, the change in pressure is going to decrease, right? So we will get a change in pressure depending on what we are doing with our pipes and area sizes. So through this exercise, we could start to understand what is going to happen with our pressure if we start changing some of these variables. So using this equation, we know our constant variables. We know the viscosity. We know that the flow rate, we have the area, so we can actually calculate the pressure change we're gonna lose across a certain pipe length, right? Now let's switch gears here a little bit and start talking about vacuum forces. So one of the first questions, so how high can a pump pull a column of water? Can it pull it forever? So the answer is no. So pure vacuum is essentially the absence of force. So when suction is applied to a pipe, what is really happening is you are removing the atmospheric pressure from the top of that liquid that's in contact with the pipe, right? So the liquid is then pushed up the pipe by the atmospheric pressure applied to that water that is outside of the pipe. That's the pressure pushing force. And with the absence of pressure within the pipe, then that pipe will rise to a certain height, right? So therefore, the height of the water in the pipe cannot exceed that of atmospheric pressure normally applied to the liquid surface. So atmospheric pressure can be thought of, it's as nothing more than the weight of air above a liquid. We always have constant atmospheric pressure pushing down on us, pushing down on objects, and pushing down on water. So your atmospheric pressure in the absence of this force is only going to get you to about 32 feet height of water. So no matter how big a vacuum you have, if you get to zero air inside that pipe, you have hit full vacuum. Once you hit full vacuum, atmospheric pressure takes over and rises the water, roughly to 32 feet. So if I no longer use vacuum forces by putting my pump over the water and try to suck water, and trying to suck water towards me, but instead, what if I place my pump in the water and use pressure? Well, now the water the water to be pumped, it can essentially reach as high as we want. But with a vacuum, you can only go as far as atmospheric pressure. So let's define a little bit on density. So density is defined as the degree of compactness of a substance, right? So in other words, it's the mass of the substance per unit volume. For example, what's the density of people in a room? You take the amount of people and divide it by it could be divided by the volume of the room. The same thing with what would be the density of people in a pool. So how does this relate to the density of the liquid? Well, every liquid has a mass associated with it, and that mass is associated with a certain volume of that. And that is what's referred to as density, usually in units of weight per volume. Weight per volume equals density, right? So then specific gravity is what we get when we relate in a ratio other densities to water. For example, to find the specific gravity of a solution you're interested in, you take the density of that solution, divide it by the density of water, and you get your specific gravity. So, for example, if I find the specific gravity of mercury, which has a density of around 13.6 milligrams per liter, and divide it by the density of water, which is 1 milligram per liter, well, that gives us a specific gravity of 13.6. So we can also be given the specific gravity of a certain chemical solution, and we can find its corresponding density because we know the density of water to be 1 milligram per liter. And this can change, the units of the density of water can change correspondingly. So some of the conventional water, business units that we use for flow rate, gallons per minute, cubic feet per second, million gallons per day. For velocity, feet per second, miles per hour, etc. For head or total head, total dynamic head, that's feet of water. For pressure, it's PSI, bar, pascals. Note that this, for pressure, this is the gauge pressure. So your gauge is calibrated to start reading pressure after that of atmospheric pressure, meaning that the gauge is zeroed out at atmospheric pressure, right? For that of concentration, for actions such as chlorination, adding fluoride, that's measured in milligrams per liter, parts per million, parts per billion, micrograms per liter, etc. And for density, as we just talked about, it's grams per centimeter cubed, or a weight per volume, kilograms per meter cubed, pounds per gallon, all density. So some below are some of the units that typically need to be converted. That's gallons to million gallons, parts per million to parts per billion, vice versa, milligrams per liter to parts per million. All these are some conversions. So let's take a look at one of these examples of calculating parts per million of a chemical. Now we need to calculate the parts per million of a chemical. So the equation for parts per million is equal to the pounds of the chemical per million pounds of water, right? So now let's take a look at a certain situation. So let's assume the following. Let's assume we are pumping 15,000 gallons of water today, right? We use 35 pounds of sodium hypochlorite during the time. And here's the data that we're given about this solution. So we're given a density of 10 pounds per gallon. We're also given a concentration of chlorine by weight, which is 12.5 pounds of chlorine by weight, right? So with these, what we first have to do, we have to get these in the, we have to get the gallons of water in the correct units. So our equation calls for million pounds of water, right? So we have to first do the conversion. 15,000 gallons, 1 gallon is equal to 8.34 pounds. This can be found on the formula sheet that we have on our Eagle website for exams, to give us 125,100 pounds, right? That's pounds of water. So now our next step, we want to convert those pounds of water to million pounds of water. Convert those units, right? By taking that 125,100 pounds, we use 1 million pounds in 1M, or 1 million pounds. So we're just basically changing the unit format to give us 0.1251 million pounds of water. Okay, so we have this part of the equation. We have the million pounds. So now what we want to do is we want to find the parts per million. So we know that the solution is 12.5% chlorine, pure chlorine by weight, right? So if we take that 12.5% and we multiply it by what we used, which is 35 pounds of sodium hypochlorite, right, during this time, we can then find the amount of pure chlorine that's being used. And that's what we want to use in our equation for pounds of chemical. That's pounds of pure chemical that we're using. So recall the parts per million equation. Again, parts per million, pounds of chemical over million pounds of water. So we have the 4.375 pounds of chemical divided by the 0.1251 million pounds of water. When we plug that into our equation, we get 35 parts per million. And with that, I will pass it on to the next presentation.